On today's episode of Survival Dispatch News, we're discussing EMPs once again. Today's video is brought to you by Energy. They're an Idaho-based company that makes some of the most rugged power stations that we've ever laid hands on. They've also won several DoD contracts, which is one heck of an endorsement. On top of which, they have a focus on EMP protection that we have not seen from any other power station manufacturer. Check out the link below for energytech.com if you'd like to learn more. And we're back. We're joined by Nick from It's Just Sharp in Utah.
Hey there.
Steve from Anything Outdoors with Steve. Is that correct?
That's correct.
Okay. And you're also a licensed electrician, correct?
I am. Yes.
Okay. And we've had a bunch of exchanges, and you clearly know a lot more when it comes to electricity and EMPs than I do. And thank you very much for coming on the channel and sharing some of your knowledge. So we just did an episode last week on Survival Dispatch News on EMPs. Got a lot of comments, including yourself. And let's just start there and get us started, Steve.
All right. Well, thank you for having me on. As you mentioned, my background is as an electrician, and I'm hoping I can clarify some of the details and some overlooked properties of the EMP and how the effects are mitigated on Faraday cages. And so we can kind of break it down to a basic level. My wife always says that whenever I start explaining things, I go into too much detail, and she quickly loses interest because I get too technical. So anytime your eyes glaze over, stop me, let me know. I can clarify, I can rehash out some of the stuff that we're addressing here. So we're going to discuss EMPs in the basic subject of it and how to mitigate the voltage spikes from that. So let's see, the EMP and CMEs, so it depends on what you want to protect for, are two different beasts completely. EMP nuclear generated blasts have a very high voltage spike, and now we've got things that are called super EMPs that it's still theoretical. Nobody knows what exactly that may pertain. The threats are up to 200,000 volts per meter. Wow. And yeah, so that, I mean, the basic military standard is 50,000 volts per meter. So that's what they try to protect against. And so there's three waves. Oh, sorry, go ahead.
No, I'm just curious, what would cause one of these super EMPs? Like, what would the potential source of that be?
That's going to be also a nuclear generated pulse. Yes. So high atmosphere burst. They send a weapon up into the air, it explodes, and what it starts doing is it sheds electrons off the atoms and causes a static electricity in the air. And instead of like a lightning bolt, it's more of a blanket where it just covers everything. And so there's a lot of factors that come into play with this, and we'll try to discuss some of it. I'll try not to jump around too much and forget some of the stuff because I tend to do that. So
not a problem.
Yeah, I can break the EMP pulse down. And I think you guys may have done that on the last episode where you've got the three waves of the EMP pulse, the E1, E2, and E3. And E1 is the initial spike, and that's starting at about 5 nanoseconds, and its duration starts to mitigate off about 150 nanoseconds. So it's a very short duration pulse, and that's the one that has the highest energy. But being that, it's also the hardest to protect against because you've got a high voltage spike that transfers to everything conductive. So all the power lines.
Would you think of that as something like being close to the epicenter, essentially?
The distance from the center of the blast has a huge factor on the voltage. Right. And so we'll discuss that in a little bit too, that essentially distance has a squaring effect to the pressure wave, just like with sound. So for every foot distance, it's got a squaring effect to the decibel range. Okay. And we can cover some equations too, or I probably just tell everybody to look them up, and I'll tell you what to look up, because the information, knowing what to look up is more important than some of the information in itself, because then it gives you a greater understanding of what you're actually dealing with.
Makes sense.
And there's a lot of information, and like I said, I'm going to try to keep it as general as possible, but I can go into depth with some of these as well. But so the E1, we already covered 5 nanoseconds to about 150 nanoseconds. The E2 wave covers part of that already, so it's already starting while the E1 is mitigating away. So the E2 will last up to 2 seconds, and then the E3 wave, I believe that one is about, I'm trying to think here. A lot of information. So that'll last several minutes. Okay. So that one has a gap between the E2 and E3. So the E2 mitigates after a couple seconds, and then the E3 will start in. And so you've got a little time to deal with that, but there's devices out in the field that people sell that will give you an alert for the E1 to tell you to turn off your main breaker in your house to try and mitigate some of that, because the electrical grid is what's affected by the E3. And so everything plugged in gets that spike. So
just in your opinion, how effective would those devices be? I mean, if you're right at close to where a nuclear attack is, I'm assuming you wouldn't have enough time probably to react in most circumstances.
And yeah, the closer you are, the faster this happens. So that's only effective. And you know, I have to look at it as an electronic device itself. Is it protected against the E1 wave by itself?
Oh, great point.
So, yeah, so you don't know. And so some of these devices that people are selling as EMP shields, you just really don't know until you have that event happen. Because again, the theoretical 200,000 volts per meter, that's huge. I mean, we just don't know what that really means until it happens.
So I'm thinking to myself as well that there may be some confusion even at the highest levels initially that, you know, what just happened, you know,
yes,
before they actually determine it was an EMP.
Yeah, your lights go out. You don't know what's going on. You look at your phone, several seconds have already passed. That E2 wave has already happened. And you look at your cell phone, it's dead. I mean, are you thinking clear enough to go run to your panel, start opening up breakers? Probably not.
Yeah.
So that's where the EMP suppression kind of comes in.
Okay.
And but I mean, you think about the 50,000 volts is what the military standard is, what they try to protect for. You know, over 100-meter line, you're looking at 5 million volts. And so that in itself, I mean, a simple device like a plug-in adapter can have several meters of wire in it. And so those alone are generating high voltages, and it's just a simple transformer. So anything that comes into the primary goes out the secondary, and that fries any device plugged into it. And same with your cell phone, you know, your little 4-inch cell phone, it's getting as much as 5,100 volts on a 50,000 volt EMP. So wow. The device itself, and not even including the electronics within, because there's antennas, charging coils inside for the induction chargers that you put them on, all those are receiving a higher voltage because that's a long coil of wire internal. The circuit board itself too.
Real quick, so if just making sure I understand this correct, you're talking about the E1, E2, E3 waves. And yes. So as you're describing, I was sort of picturing like waves coming onshore from the sea. You have one, and then the next one will come, and then the next one comes, and there's a gap in between. But I guess, is there a certain duration that each lasts? Is that dependent on power? Or is there a standard that like E1s typically are 200 milliseconds and E2s are 500 milliseconds, or is there sort of a difference in range here that would pertain to each?
It is a standard. Like I said, the E1 is 5 nanoseconds to 150 nanoseconds, so it's a very short time period. And that's mostly based on how the nuclear device works. And nuclear devices, and we'll get into this in a little bit too, they're running off a different frequency, which is what dictates that wavelength and how long the duration is for each one. So that has a great factor to it. And that's why solar CMEs are a completely different beast in themselves. And so you're really inducing maybe about 5,000 volts per meter. And it's a way different frequency as well. And frequency is a big part of how you mitigate this. So we'll cover that in a little more extent too. But yeah, so they do have a general rule by that frequency on how that reacts to the length and duration of each wave.
So is there a way to create an EMP for us other than a nuclear bomb, or?
They've got devices to do so, and they're not really accurate, is the best way to put that, because the frequency is the biggest portion of this, and we'll discuss why. And that's why some products won't work and others will. Okay. You start looking at the military standards, and they want a continuous shell. All seams that are overlapping have to be a continuous weld to complete, no holes, okay, and all seams are covered. And there's a reason for that, and that's the frequency. Okay. The nuclear EMPs are running at such a high frequency, and that allows it to transfer through any small holes in a Faraday cage. So what typically would work well for a CME is not going to work at all for an EMP. And so that's what we have to kind of discuss a little bit. And CMEs are so much easier to protect against, because you're working with a smaller voltage and a lower frequency. So it's a lot easier to really mitigate those. And so simple devices will work well. You know, the old garbage can, that can help against some of that stuff.
Okay.
Yeah.
So, you know, I think there's a bunch of information out there saying things, you know, like using wire mesh and stuff like that on the inside of a room. And then when you and I were corresponding offline, you said that's not really applicable for EMPs.
Yes.
So would that be applicable for a CME potentially, but not a EMP?
Absolutely. Yeah, okay. Absolutely. And I can go into some of the numbers here in a little bit too. Actually, let's see, like AM radio, that's about a 10 kilohertz wave. And so that wavelength ends up being 30,000 meters. And so we'll keep everything in meters just to keep the math simple. Okay. So we'll discuss how that wavelength is affected by the hole size of a Faraday cage. So you got AM waves at 30,000 meters. FM waves are about 1 megahertz or 300 meters in length. And so you'll see how those numbers, you've got 10 kilohertz, 1 megahertz, they all keep that 3 number. And it's actually 299 meters. So I'm just rounding up to 300, make it easy. Cell phones, when you're making a phone call, is about 1 gigahertz. And so that ends up being 30 centimeters. So now we're working into a wavelength about like that.
Okay.
And Bluetooth and Wi-Fi, that's typically your 2.4 gigahertz. And even your microwave, the frequency inside the microwave to cook your food is the same 2.4 gigahertz. And that's 12 and a half centimeters. And so now we're down to there. 10 gigahertz is 2.9 centimeters. 50 gigahertz is 0.599 centimeters. And 100 gigahertz is 0.299 centimeters or 2.9 millimeters. So you're, little tiny hole.
Okay.
The rule of thumb for frequency on a Faraday cage is 1/10 of the wavelength. So if you've got an EMP pulse that's generating 100 gigahertz, which is roughly what their range is. So we're we're between 10 to 100 gigahertz of frequency is generated from an EMP. And so the rule of thumb being 1/10. So if you're working with a 2.9, 1/10 of that is 0.29 millimeter hole is the maximum you're allowed to stop that frequency to mitigate that voltage.
So essentially, you know, as the frequency rises, the size of the opening in your Faraday cage just keeps shrinking down.
Keep shrinking down. Yes.
Okay.
And so that's where CMEs are so much easier because they're working at a lower frequency. So you can have a 5-inch hole with a CME and still be protected. So
Wow.
your chain link fence, perfect for CMEs. So it just depends on what you want to prepare for. Now, if you're looking at the nuclear blast, that's a whole different beast. And now you might as well figure if it holds water, it can protect against most EMP pulses. So, you're dealing with small holes. So take a container in any direction that if it holds water, it'll be protected. And then we've got a whole bunch of other factors included with that too. But yeah, so there's a whole lot of information, but it looks like you have a question.
Well, no, I was just going to say, there's always an interesting comparison between electricity and water. I can remember when I was young, my father saying, that the garden hose with a sharp stream is like voltage, whereas the really powerful energy in a river is more like amperage sort of thing. And you're not the first electrician I've spoke to who compares things to water. I was actually thinking to myself earlier that I looked up some images of an EMP coming in and how it kind of envelopes things, like an EMP or a Faraday cage or something like that. And it's still like water. And then, of course, Nick made a comment with regards to waves of it. I think it's a good way to visualize, for me at least, the relationship, between all these different things that are, electric.
Yeah. And I was kind of referring to an EMP as being more of a blanket effect where it just covers everything. You've got a lightning strike that's localized to one spot. This is everything. So anything conductive within its path will start accumulating this voltage. And so you'll start to see things if you're outside, metal objects starting to get little lightning strikes off of them as they're increasing this voltage because it's able to jump that air gap.
Amazing.
And so 5,000 volts, you can jump a 1-inch air gap. As it starts to build millions, it's going to be jumping all over the place. So you'll start to get a coronal glow off of some metal objects that are further from the ground until they gain enough electricity that they're starting to jump. So it'll look somewhat like a Tesla coil as it starts to spike out electricity through the air and then to the ground.
That's actually the visual that I just got. That's good.
Yes. Yeah.
I spent a little time when I was in college studying sound, and you'd related it to it earlier, and I had a thought. One of the things we always talked about was this reflectivity in certain materials. And it's something I saw in several of the comments. I was taking some time to read through them and people asking on, okay, what about different kinds of surfaces? Is it reflective in any way? And does, having different layers sort of protection or different layers of different materials, does that help you? And I was thinking back to my time studying sound and that, if you had a piece of concrete or a piece of plywood, sound transferred through it differently or it didn't over a certain depth. Is that similar in your size of hole? Can people put a layer of tin on a roof that might change the effectiveness of that frequency through it, or how thick a material is? Does that have that same transferability that like sound would have?
Yeah, that's a good segue into EMP suppression and how that is affected. So when you're looking at EMP suppression, you're measuring this in decibels of attenuation. The basic rule is for every 20 decibels of attenuation, it'll equal to 10 times less energy in voltage. And you can look this up too. There's the 20 log equation. So all these logarithms, there's a 10 log for voltage and a 20 log for voltage and sound pressures. And so the 20 log 10 or the inverse square law. And this includes distance as a factor as well. So they typically use that 20 log 10 rule for determining distance for speakers to make sure that they're balanced properly. And so you'll see this a lot in large sound setups where, okay, this speaker's 10 feet further from the audience than this one. How many decibels do I have to increase that one speaker to then match audibly the same as the other speaker that's closer? Since it's an inverse square law, distance is a big factor, and that's same with EMPs, is the distance from that pulse is a huge factor on how much pressure it has. And the reason it's inverse square law is think of it as a cone. So from the source, it's going to be the highest. And as you're traveling out, that one square becomes 9 squares. So now you've got, a larger surface area, but less voltage within that surface area. And so the further out, it's got that inverse effect because that keeps growing another layer larger. And so you can reference that inverse square law and utilize that in an equation to determine a guesstimated volts per meter and what you want to attenuate it down to, and how many decibels are required to attenuate it down to a usable voltage that's not going to damage your devices. And so there's other factors that come into play as well, but the less energy on some, there's some devices that are super sensitive, like diodes and transistors, that will blow, microchips that will blow with just a very minimal voltage. And so those require a much more hardened Faraday cage than something like a drill motor, where, you've got a long coil of wire in here, but the insulation in that coil is rated up to 600 volts. And so it's a little easier to drop that down to a 600 volts instead of half a volt that you're looking for some of these microchips. And so it doesn't require as much of a Faraday cage to get down to that voltage. But you also have to keep in mind, it's a long length of wire in that motor winding. And so now you've got to add in the length of wire and how many volts per meter that actually adds up to. So you can bring it down to half a volt, but you've got 30 meters of wire. And so now you've got 1500 volts, before you know it, it adds up fast. And so you just have to do the equations and figure out, okay, this has an insulation property rated up for 600 volts. So how do I drop below that? And that's what you have to look at to bring the decibel rating down to mitigate that voltage.
So, and I have a layman's question for you.
Sure.
So in the high tech world, I was with the Sun Microsystems Oracle for years. Larger customers with larger data centers would have dual power conversion units that would take the current coming in from the provider and flip it from AC to DC back to AC with a very clean sine wave, and a consistent 120 volts. And those devices typically are, fairly expensive, much more expensive than just a UPS, for example. Yes. Would that provide any mitigation, or is it going to blow up?
Well, that is what they consider an isolation device. And so you're isolating, and you're able to easier clean that frequency and voltage spikes because of that isolation, but it's limited as well. So it's used to dealing with 10, 20, 30 volt spikes where we're looking at hundreds of thousands of volts. Gotcha. Potentially. Okay. And so in a perfect world, yes, it'll help. But when we're talking EMPs, I'm struggling to find any information on devices that will actually mitigate this properly. Okay. And, I was researching the whole house surge protectors and just your standalone unit surge protector or power strips that have the surge protector built in. And those are using a metal, what's it called? Oh, I'm drawing a blank. They're using a device inside of it to mitigate some of that voltage, and it'll probably come to me here in a minute. But
but I'm guessing in Central Florida, of course, we get some pretty violent lightning and thunderstorms.
Yes.
If you followed our channel at all, you've probably heard me say more than once, we're a first world country with a third world power grid. And
absolutely.
Our particular part of Florida is serviced by FPL, Florida Power and Light. And I don't remember what the charge is, but they will come and, put a so-called surge protector on your meter outside. And if you don't have that surge protector and anything is damaged by anything that comes through the grid, then, they say they're not liable for it. But if you do have that surge protector and something goes down, and I haven't tested this, but they say that they're willing to replace stuff. And it might be, a fabricated lie for all I know. I don't know. But yeah. They must have some belief in the product that, it's going to provide some level of mitigation, or maybe not. Maybe they're just ripping people off. I don't know. But
yeah, and it does help. Typical surge protector, the power strips are rated in joules. You'll see those go from anywhere from 400 joules up to 5,100 joules. And that's how many volts it'll dissipate in a second.
Okay.
And so it's just the ability for it to dissipate these spikes of energy. And once it exceeds that, it actually destroys the device. And then it makes anything downstream of it susceptible to that voltage spike. So the higher the joule rating on a surge protector, the better protection it'll offer. And so you're looking for a device that will have a high joule rating for lightning strikes. The closer the lightning strike is to your house, again, the distance, the more energy you need to dissipate at a rapid rate.
So backing up a little bit, then the energy is so significant from an EMP that there's nothing out there.
I don't believe so.
Gotcha.
The whole house units, they change it up. Instead of rating in everything by joules, they're going by how many amps it'll allow it to dissipate. And so some of the like the EMP guards or whatever they call those devices for the whole house panels, they claim up to 200,000 amps of current that it can dissipate. And again, I'm not sure how accurate it is because, again, it's an electronic device and I don't know its susceptibility to an EMP on the E1 side of it, not even making it to the E3 before it fails.
Gotcha.
And so not knowing that, I can't say, yes, this one device will help you. I do have surge protectors on both my meter base and my house panel and my shop panel, and all three combined will help mitigate cumulatively any surge that comes in. So each device, even though it's located further away for a far away strike, each one will help mitigate some of that amperage and voltage spikes coming through the line. And so that works great for something small like that. And it'll even work for a CME effect where you're not dealing with as much voltage spike coming in. And but really, as you mentioned on your last video, the only surefire way is to have a device that's not plugged into the grid. Right. And that's the only device that will probably survive an EMP or some CMEs.
So quick question there. Somebody made a comment on the last episode that if a device had an external power supply, so just for people who don't know what I'm talking about, you've got a cord that you plug in and then there's a block and then there's usually a barrel on the other end that you plug into your device. And that person's comment is that if something was plugged into the grid and it had an external power supply, that the power supply would be toast, but the device itself would survive. And it seems to me like there's not enough mitigation there for something at the magnitude of the EMP. Okay.
Yeah, there really isn't. Okay. And so that external power supply is the same as your transformer packs. Anything with a block like this is a transformer pack, and that's your isolation device. Same with a laptop, that's an isolation device, and same with that DC to AC converter you were referring to earlier. Okay. It's a electricity isolation. The downside to this is the primary coil is transferring the same voltage to the secondary, just not to the same degree. And so when you're transferring back and forth like that on the DC to AC version, you're actually mitigating some of that in each process. That external power supply that they're referring to, we're talking, again, thousands of volts, and 5,000 volts will jump a 1-inch gap. So that device having all those components inside a case so small, it'll easily jump voltage from one side to the other. So the device itself can be completely fried and it'll still jump across. And what the problem is it's looking for difference in potential. And so we'll discuss that in the Faraday cage as well, and why you need to insulate the inside of the Faraday cage from that difference in potential, because whatever you put inside the Faraday cage has a difference of potential from what the outside is receiving. Okay. And so that device has electricity jumping that gap easily. And with 50,000 volts, say it's just a 1 meter, 50,000 volt spike, it'll easily hop that gap. And there's not a whole lot you can do. And so again, anything plugged in more than likely is going to be gone. And
So,
there's not a whole lot you can do about that.
so I don't mean to jump ahead, but there were also
That's fine.
some comments on the last video where people had taken a metal, trash can, whatever the case may be, and then they either lined it in rubber or cardboard,
Yes.
something like that. So that's like decreasing the conductivity potential, what you're
Yes.
getting at, but probably would it be enough to protect against an E1?
Rubber?
Yeah.
Yes. Rubber, yes. Cardboard, no.
Okay.
Cardboard is essentially the same as an air gap. So it'll easily jump right through cardboard, no problem. Rubber is insulated better. Ceramics, again, are really good. Polyethylene is like those plastic buckets.
Yeah.
If you've got a continuous shell of polyethylene, and that's the key, is having a continuous shell of it. So it's got to be a complete container with no holes, because that hole is an air gap and it's searching for that difference in potential. And so it'll jump like right across.
Yeah, something with a threaded lid or compression. Yeah, that's really useful information. Thank you, Steve.
Yes. Yeah.
Something
so
like a waterproof bag, Ryan, that's set up in rubber. Is that the same idea where that takes that top and rolls it over, makes that watertight? If we're going back to that water.
Yeah,
thing?
That's a very thin layer. So we're looking at something that's a little more substantial, maybe 20 mils or greater, to offer a decent resistance to that electrical jump. And some of those bags, I know you may not see them, but they've got small holes in them. High voltage will jump through small holes. When we're testing electrical equipment, we're using what's called a megger, and it increases the voltage by 1,000 volts or more just to find those little pinholes in insulation. Wow. And if it fails that test, then it's a fail on that system. So we've got to make sure that whenever you're making connections on high voltage things, high frequency things, that they're completely sealed. And so you're doing lots of wraps of electrical tape just to make sure that there's no pinholes for electricity to find a way out. And the higher the voltage, the easier it is to jump through that little pinhole.
Very interesting.
Same with the protective equipment, rubber gloves, whatever you're using, they're rated to a certain voltage, just like what you were talking about on your last episode. Bulletproof vest is rated to a certain caliber. And so those rubber gloves, even though it's a layer of rubber and it's insulating, it can only stop so much voltage before it jumps through the glove as well. So some of them are rated 600 volts, maybe up to 1,000 volts. And beyond that, it can still find little pinholes within the molecule structure of the rubber and find a way out. So, yeah, it's scary stuff.
So, awesome explanation of things, Steve, and really appreciate the information. I'm assuming, you've got, some stuff already put together for your discussion points. But I think kind of like the biggest one would be, what's your average person? What's the best thing that they can do?
Well, since we're talking the suppression portion of it, the container that you're using, aluminum foil, like what's in your kitchen, that thickness of aluminum foil will have up to about a 90 decibel attenuation. So that's a huge attenuation for aluminum foil. Now, given that attenuation's at about 2 gigahertz. So once you start getting up into the 100 gigahertz, it's less effective. So it's maybe not able to keep up with that. So it might drop it back down to about 40 decibels of attenuation by the time you get up to those levels. So that frequency has a huge factor portion of this. But Faraday cages are cumulative. So the more layers you have, it's a sum of all those layers. So you can have a large Faraday box with another Faraday box inside. So each container, it's the sum of all those containers and what they're able to protect against. And so that's when you start to look at what you really want to protect. And keeping in mind the entire electrical grid is going to be affected. So there's some things that you're just not going to save. So your TVs, your air conditioners, your furnace, some of those devices, it's just not possible to save them. You can keep components of those in a Faraday cage and be able to replace those components. But even the motor itself will have such a large spike on the windings that it'll probably blow through the insulation and make that motor not usable. And so you start to add up all these devices that you have to save in a Faraday cage for the potential of replacing all those. And then you run into the next issue, a follow-up attack. so you start pulling stuff out of your Faraday cages, and there's another EMP pulse that goes, you're wiped out. So you kind of have to give it some time, like maybe a few weeks before you start really pulling stuff out of your Faraday cages. And because you don't know, I mean, if this is a nuclear attack where they're sending EMPs to disrupt the grid, they're not going to just stop at one. They're going to do several. So if that's what your goal is to prepare for that type of scenario, you really do have to say, okay, this is not the one and only attack. They're probably going to follow up with more. And so you start maybe waiting before you pull things out. I mean, you can pull some stuff out and make like for communication and talk to other people real quick, and then put it back in and close everything back up because there could be a follow-up wave. And same with that wave 3. That one starts coming in for several minutes. So you don't want to pull things out right away either, because that third wave will hit and start affecting some of those devices as well.
Man, that's awesome information, Steve.
Yeah. Being additive for those Faraday cages, that's the biggest help for us. Anybody that wants to save devices, putting them like the ammo can aspect. I've got a large ammo can. It's about 1 meter tall. And keep in mind that meter is also getting the same voltage. And so that's why you have to have that insulation barrier from that can to the device inside. And so you're getting 50,000 volts on the can. Everything inside has a difference of potential. It's a high likelihood that it's going to arc through in different portions of that can if it's not insulated. But doing things like anti-static bags inside, it not only adds another layer of EMP decibel rating to it, but also helps mitigate some of that to the surface of that bag instead of through the item inside of it. And so for every layer like that, where you can have an insulating layer and then another conductive layer, insulating conductive, makes a huge difference. And so it's more than just the thickness of one layer. It's having those multiple layers with insulation in between. Each one kind of brings that voltage around that surface of those layers. And so it makes a huge difference on what's being protected. And again, the device that's being protected requires different levels of protection. So your microchips and diodes and transistors, those are the most susceptible to the even small voltages. 5 volts can take them out. And so that's where you have to start bringing that decibel rating up to lower the voltage. And so using that square.
Go ahead.
Go ahead.
No, I was just thinking in terms, there were some comments and questions previously on this very topic. And I was just thinking to myself, what would be, doable for the average person without breaking the piggy bank. So if we had this metal container, ammo can, whatever the case may be, that was properly sealed, and then inside of that we had something that was rubber that was properly sealed, and then we were protecting a ham radio, let's say, that was inside of a Faraday bag inside of that. That doesn't sound too unreasonable for the average person to put together.
No, and really you can use inexpensive materials as long as they're properly sealed, properly conductive between all the gaps, all the seams. Using something like aluminum tape, where you can tape up the seams and make it a continuous product throughout. So using that aluminum foil theory. But you also have to keep in mind it's got to be durable too, because if you poke a pinhole in it or sliding it around on the floor, you're going to tear some of that. And so you want it to be durable as well. And but sealing up all those little pinholes is key to having a proper Faraday cage for the high frequencies. And then multiple layers again, that's really helpful. But there's different devices that people have talked about using, like microwaves, and a microwave is running about 2.4 gigahertz. That's kind of like the magic number for everything. So you look at the mesh on the door of that microwave, and you can see the hole size, and so that's effective for that 2.4 gigahertz. And but when you start going to a higher frequency, it's no longer effective. So people think, oh, I'm going to put my stuff in a microwave and close the door, it'll be great for a CME. Not so good for EMP.
Okay.
And those, that needs to be an understanding when what you're wanting to protect, once you understand that it's not protected because that frequency. So it again falls back on what you're trying to prepare for. And we're not imminent for a nuclear attack, but it's a lot closer than what it could have been a few years ago. So, it's looking like you want to start protecting more and more devices. And so that's when you start looking at that list of devices you want to protect. And so you want to make a list of critical components or critical devices. And communication tends to be one, power generation, solar panels, really gas generator. If you've got an ability to make a room that's EMP proof, and you can use inexpensive products like just a foil barrier. I mean, this is actually perforated to allow moisture through, but if you do 2 layers of that, or the foam board with the aluminum coating on it, you start adding up layers like that, where the exterior has that foam board with taped up seams. Again, you have to tape up those seams, tape up the nail holes, tape up everything. But once you do that and have a continuous shell of just foam board, which isn't horribly expensive, you're maybe $20 a sheet for 1-inch foam, and it doesn't have to be super thick foam, just you're looking at that aluminum layer. It's nice having the added insulation if you're putting it on a structure, but it's kind of secondhand if you're looking at EMP protection. So
if you had, one or multiple of these folding solar panels that, typically are used with a portable power station, and it wasn't plugged into anything, it would still be vulnerable.
There was a person on YouTube that had made himself an EMP generator and put things in this generator to test. He put in a laptop and a solar panel, and an unplugged solar panel survived his EMP generator. Now, we don't know what voltage that's dealing with, what frequency that's dealing with. So I'd like to be able to say that it could survive, but keep in mind, a solar panel is essentially diodes.
Yeah.
And so you get a reverse current across those diodes and it takes them out. And so being unplugged is huge. I mean, that's the biggest factor, because that length of cord going from one panel to the next to your charging controller, that length is huge, because we're talking more than a meter. So 50,000 volts will take out a solar panel. And but the diodes within those solar panels are susceptible to the EMP pulse as well. And I would love to be able to say that, sure, it'll survive, but I really don't have an answer for that, whether or not it actually will. I personally would, using inexpensive materials, whether it's foam board or foil wrap or anything like that, making a continuous shell around a structure, put things in that structure in an EMP Faraday bag, whatever it may be, that you create inside that structure as well. And I'd be willing to say your outside foam board with the aluminum coating, do the inside with foil wrap. I mean, this is inexpensive product too. I mean, you can get a fairly large roll of it for a few $100s and cover a small structure really inexpensively that way. And maybe for a $500 investment, have an 8x8 shed that's completely protected, and put your generator in there, put some power tools that are a big one, because nobody really thinks about the power tools, and different electronics that you don't use daily. And so that's when you start getting into this other issue, is daily use items that you don't want to continually open and close these Faraday cages for daily use items. You want them to kind of remain there. So if you have extra devices to put just for that scenario. And that's actually your biggest expense of having the extra devices, extra circuit boards, and extra parts to replace things that do get destroyed.
I'm just thinking in terms of, the tech world where, for, disaster recovery planning, we always preach to people to have backups of your backups,
Absolutely.
So, it seems applicable here as well. So how about one of the big shipping containers that's all metal and maybe welding some seams on it and building layers inside of it?
They've all got vents on them for pressure. So they've got these pressure vents. So as it's changing temperatures, it's changing pressure. So you kind of have to have some sort of venting still. So when it warms up, it doesn't just pop, but you have to close all those vents up and maybe doing just a little pressure valve that remains closed until the pressure changes in both directions. So you've got a pressure valve that's usually sealed, but again, you want to have another cage inside of that.
So let's go low tech. I mean, what happens if you dig a hole that's 5 foot deep and you put your stuff in there and put the 5 foot of dirt back on top of it? How does that work?
Okay. So ground, highly conductive ground, there's a way to meter between 2 ground rods that you drive into the ground and put a meter across and see how conductive it is. If it's down around 1 ohm, that's highly conductive. So this highly conductive ground will offer about 30 decibels of attenuation. And so you can add that into your equation as well. So
not enough on its own.
What's that?
Not enough on its own.
Not enough on its own, but you put a metal box underground, you're adding that 30 decibels on top of 40 to 80 decibels. And now you're into this 120 decibel range where you can protect against a 200,000 volt per meter EMP pulse.
Okay. I was just going to ask you for that guideline. So if these, if that upper echelon, that 200,000 volts is actually, possible.
Real. Yeah.
I was going to ask what level of protection in decibels do we need to get to? 120s?
Okay. Yeah. So the equation is every 20 decibels is a 10 factor of reduction. So your 200,000 decibels with 20 decibels of attenuation, you're now down to 20,000 decibels. And so the next 20 decibels, or sorry, I meant volts, volts per meter. So the next 20 decibels will drop it down another, down to, what was that? 2,000 volts per meter. So at 40 decibels, you're down to 2,000 volts per meter. So it really does have a big factor on that Faraday cage and how many layers you have too. But ultimately, for a 200,000 volt per meter EMP, you're looking at what would that be? About 2 volts per meter at 80 decibels, or 0.2 volts at 120 decibels. So that's what you're looking at, is trying to get that number as small as possible. And then again, keep in mind there's a coil of wire in here. So that 0.2 volts on 1 meter length of coil, now you're getting that back up again. But for a lot of the electronics, they probably will survive that 0.2 volts. The military standard being the 50,000 volts, they like to do 80 decibels of attenuation to drop it down to half a volt to have their equipment survive. So they're looking for that half volt spike per meter. And keep in mind, that is per meter. So it's half a volt per meter of any conductive materials within this EMP cage. So even though you're dropping that around the shell, that huge voltage spike, you're still getting voltage inside. And so that's, I would say, if you're looking at attenuating a 200,000 volt per meter EMP pulse, look at about 120 decibel attenuation. And so we already discussed foil being 90 decibels. So 2 layers of foil, you're 180. You bury that foil underground, 30 decibels underground, and now you're at 120. So you're good to go for 200,000 volts. And that'll drop it down to the 0.2 volts. And so most items within it will survive.
Yeah, and fantastic. That's understandable. Like, that's in terms that your average layman like me that can understand it.
I know, and it's beautiful that it works in powers of 10s and 20s like that. 20 decibels, 10 times less voltage. So it works out well. And same with that frequency. We were working with a factor of 3. So for every next level. So you're going from 10 to 100. It's dropping that tenfold again. So that increase of frequency is making that hole size that you have to drop down, and that hole size is a factor of 10 as well. So if your wavelength is 3 millimeters, you have to drop that hole size 1/10 of that, so 0.3.
Wow.
So it makes all the math pretty easy,
Yeah.
and it just works out well, doesn't it?
Yeah.
Anytime you can save me from having to use a calculator is a good thing.
Yes. Yeah, powers of 10 all day long.
So, Steve, do you have, I know you do survival stuff, prepping stuff, in addition to being an electrician. What would your list look like of devices that you feel needs to be protected?
Yeah, that's where it becomes difficult. Today's day and age, we kind of take for granted a lot of things.
Mm-hmm.
And so even, you look back 30 years, photos, you printed out all your photos, you had film you took photos on. So all those family photos, they're now all digital, and doing something as simple as putting it on a Blu-ray disc or DVD, this is EMP proof. You can leave it out on the desk drawer. It doesn't matter. Everything's contained within this. As long as you've got a device to read it, then you still have your photos. So then you're just looking at protecting a DVD writer or burner or whatever it may be, or a laptop that's got one built in, or a computer. And so you build that room, that Faraday cage, to protect those devices that can read information. And so information is huge. Books, go back to books instead of everything electronic. I've got a series of books, and I was going to bring one out as a prop, but I kind of ran out of time. But it's essentially how to live the old way of life, because people have kind of forgotten that lost art and that lost skill. And so the modern day, you don't need it. You're not practicing it. So that is very important for really helping you through a situation like this if things even come back. So if you're looking at an EMP strike being a nuclear attack, you really don't know. And so the entire electrical grid pretty much will be wiped out. The communication grid, same thing. So all that stuff is gone. So you're even looking at fuel pumps, water supplies, all this stuff is going to be affected. And so there's only so much that you can do. You can't protect everything. And
so I read somewhere that both parties, the uni party, whatever you want to call them these days, over the years have proposed legislation to protect the power grid from EMPs. And I've heard numbers thrown around like $5 billion, which in the grand scheme of things is not a big money. But nobody has actually taken action on that. And
correct.
There's probably all kinds of political reasons for that. But from a practical standpoint, is it even a possibility to protect?
Absolutely.
It is. Okay.
Yeah. There's a way to protect the entire grid, but it is expensive. Some of the numbers I was looking at was maybe around the 300 million for a localized grid. And there are some, I think there was a place in Utah that actually did accomplish that. And I'd have to look it back up because I don't have the information off the top of my head, but there is a place in Utah that actually did have some EMP protection. And I don't know to what level they've got it protected. So that's another question that's kind of up in the air. You don't know how much protection you need for one, or how much it's able to withstand. And so that Faraday cage is huge. Having a device that opens and is able to not only quench an electrical arc, because it can jump a big gap in air, but if you've got like fuses, they are typically filled with sand to quench that arc. So even on a high amperage arc going through this fuse, after it blows the fuse, it's able to quench that arc. And so they're able to include devices like that within a power grid to open up and not allow it to destroy a transformer before it does. And so that's important.
What kind of voltage per meter would your average Faraday bag be able to withstand?
Measured in decibels, your standard Faraday bag, it depends on the bag, of course. And the standard, I think, is about 40 decibels. Wow. Is the attenuation of a Faraday bag. So you put that Faraday bag into another Faraday cage and you start adding that up. So
Not nearly enough on its own, essentially.
No, no. And then you see Faraday bags that are made out of a woven mesh metal like this, and that'll work for CMEs, and it won't work for EMPs. So that is another thing to make sure that you understand. If you're planning to protect against, and CMEs do happen, and they're more likely, I would say, than an EMP. But maybe not today. I don't know. I mean, it's changing daily. So, but
I'm under the impression that, the average prepper feels that if they buy, a Faraday bag and throw something in it like a ham radio, that they're covered. And it's interesting that it's not. It's you need a layered approach.
You really do. Unfortunately, I look at some of these EMP bags, and even like the simple static bags that electronics are shipped in. You roll up the edge, you've got a good at least 20 decibels of attenuation in that bag itself. And so that'll help dissipate a lot of the energy around it, but the electronics are still susceptible within that. So it's great for, you're walking around, you build up a static charge, you touch the bag, it dissipates that energy. And so the electronics are still good. But for an EMP,
question. Would a Mylar bag qualify as the same thing?
Yes. Yeah. So you've got a Mylar bag that you can put items in. And again, you want to insulate the item within it. And even just an air gap is helpful. So if you wrap it in fabric, that acts as an air gap. So that's helpful as long as you've got it within another EMP bag or box or container, and then another one around it. So each time you do that layering and you have at least one really good insulating layer, you're reducing that likelihood of a electrical arc shooting through that device.
So Mylar bags are pretty cheap. So I'm just
absolutely
thinking in my mind, that you take a ham radio, and you put it in a Faraday bag that you put in a Mylar bag that you put inside of an ammo can. And you're starting to rack up some decibels now. Protection.
Absolutely. Yeah. And the Mylar bag is just as good as any EMP bag that you buy on the market too. So it really is a fairly decent resistance to some of that voltage.
That's really interesting because we do some freeze drying and stuff like that.
Yeah, same.
A company just sent us these huge 5-gallon Mylar bags, and my wife and I've been scratching our heads thinking, what on earth do you put in a 5-gallon Mylar bag?
Well, you put it in a 5-gallon bucket and you fill it full of rice.
There you go.
Yeah, because really that's what you're trying to keep out is oxygen for food. So that's what you're doing is you seal up that 5-gallon Mylar bag inside a 5-gallon bucket, and you really are mitigating that oxygen approach to it and throwing oxygen absorbers, of course, but yes, it makes a big difference.
Man, that's absolutely amazing, Steve. Is there anything else you want to add before we wrap up here? I mean, this has just been an awesome day at school for me.
Well, we were kind of touching on what to put in and different devices that work well as EMPs, Faraday cages. Simple things like a paint can. As long as you've got that lid that you have to hammer on at 2 gigahertz, that offers about 85 decibels of attenuation.
Wow.
But keep in mind, we're looking at maybe levels higher than 2 gigahertz.
Yeah.
So EMP can be anywhere from 10 gigahertz up to 100 gigahertz. So it starts reducing that decibel attenuation as well. But that can be an added layer, and it's inexpensive. So you can put something inside a paint can, inside another cage of some sort, another container, and just start adding it up. 55-gallon drum with that friction clamp ring that you can open and close. That allows you to get into the container easily.
I'm looking at 2 of them out there.
Yeah. So it's a steel container, so it's not as conductive as aluminum. So that's maybe down to around 75 decibels at 2 gigahertz of frequency. But I mean, it's helpful. So all those are helpful layers. And so when you start with a large container like that, and you start putting a smaller container within it and, propping it up off the bottom, so you've got a decent air gap or a decent insulator around it for the next container within, you're getting some really high decibels of attenuation with these Faraday cages that will make the items within more than likely to survive. And so some of those layers are really important. That's why it's kind of going towards the room approach, because you can get some cheaper materials. And like I was saying, just your aluminum foil being about 90 decibels of attenuation at the 2 gigahertz, that is a really inexpensive material. Copper being higher conductivity will offer even a greater protection. So the conductivity of the item itself that you're using as a Faraday cage makes a big difference. And that's why the 55-gallon drum is a little bit lower than aluminum foil, something simple like that.
As you're describing each of these things, I keep thinking back to target hardening. So
yes.
I had an office that was broken into many, many years ago, and there was quite a bit of equipment that was stolen out of that office. And so the detective that I spoke to at the time, he said, he gave me a whole list of things, said, do all of these things, because I'm looking at y'all's neighbors here, and they don't have any of this stuff. So the bad guy's going to show up, and he's going to look at yours. He's going to see cameras all over the place, bars on the windows, multiple layers at each doorway. So you got a steel door followed by another cage door behind it. And you're just going to give up and say, I'm going to go take that easy target over there. So I'm just thinking in terms of layering, like target hardening is kind of a similar principle.
And something as simple as a spot for them to hide close to the structure, to where if a car comes by, they can hide behind a bush real quick. That makes a big difference too. Yeah, but you're exactly right. It's all those additive layers, keeping things away from your front door, like a hammer and a shovel, so they can easily pry it open, makes a difference too. I mean, it's an opportunity. So you look around and you see all these opportunities near your house of what you can use to hammer in a door. My wife leaves out these T-post drivers right next to the front door. I'm like, what are you doing? This is a 2-handled battering ram. I mean, one blow and you're in. But she doesn't think the same way. So it's nothing to her. It's like, oh, I'm just making it easy for tomorrow so I can just grab it again and go back to work.
It's an interesting topic though, because we have some bushes, some shrubs around the windows of our house that have these brutal thorns on them. And
yeah, those are great.
There's a type of palm tree that we have in Florida called a robolini, and they've got spikes on them this long, and they're full of poison, and they will mess you up. And I've put them in front of windows in several properties. Just little things like that is going to discourage somebody from even looking in the window, let alone trying to break through it.
Yeah. And so when you compare that property versus the one that's got the battering ram next to the front door, I'm going there. I mean, look at them. They're not even cleaning up after themselves. So the likelihood of having easy access to things within the house is going to be even greater.
So I have a request, Steve.
Sure.
I would like to schedule a follow-up episode of Survival Dispatch News on this topic of target hardening, because clearly it's a thing that you have a level of awareness over, and it's an awesome topic. And I agree with you. Like the DEFCON level keeps getting worse, but the chances are still probably higher that somebody's going to break into your house or something along those effects. I'd love to do an episode with you on target hardening, Nick as well, and some of our other guys. I think that's a fascinating topic, and love your input there. So
okay, well, and it falls right in line with EMP hardening, because after an EMP pulse, people are going to start hitting the streets. There's nothing left to do in your house. You're not on your video games anymore. You're not watching TV all day long, and you're starting to get hungry. So you're going to start going house to house to find out what other people have. And that's very important to keep in mind as well.
I'd like to give credit where credit's due. And I think it was Chris Weatherman, the angry American, who said to me, we are never more than 3 missed meals away from anarchy. And
absolutely.
It's one of those comments, somebody makes a comment and it just sticks with you. That one has really stuck with me. So I just want to remind everybody that your YouTube channel is Anything Outside with Steve.
Anything Outdoors with Steve.
And Anything Outdoors with Steve. I'm going to put that link down in the description. If there are things you think that people should, study up on their own, if you don't mind sending us some links, we'll put those in the description as well.
Yeah, I think if you just look at some of those equation factors, like the square root factors, some of those things are easy to look up, and it'll give you a really good baseline to understand what you're looking at for mitigation. But just using those simple rules, you figure it out real fast on what you need to do. But
so maybe if you don't mind, maybe if you could send those to me offline, like the basic equations that we've covered, so I don't make any mistakes. I want to make sure that we pass on accurate information to our audience.
Yeah.
And you know, if everybody who's watching this, go check out Steve's channel. If you need to sharpen your knife, make sure you go check out Nick's website. It's just sharp.com. And appreciate y'all's time coming on here. Steve, that was
one last thing. I would implore people to make a critical list of components that they do want to kind of protect, and go over that and see what's viable to save. I mean, even simple items like LiFePO batteries or lithium batteries, they've got built-in circuitry that people don't think about. And so components like that you want to survive an EMP, that's what you're looking at protecting. And so make a list of what's important, what critical use items you may have in your daily life that you want to survive.
I'll be honest, I had not even thought of protecting pictures and whatnot, Steve. I mean, that wasn't on our list. It is.
I know. I'm always kind of oriented family first, and some of those things that you just don't think about that you kind of expect to always be there, gone.
Yeah, so
we don't have backups.
So I foresee that we'll probably put an article up on survivaldispatch.com with some suggestions, and people can use the checklist. I'd like to get that up there as well. And really look forward to discussing target hardening with you. And you know, we'll wrap up there for today, but really appreciate you coming on, Steve. That was extremely educational.
Thank you. Yeah, thank you for having me.
Absolutely. Well, hopefully we have you back again soon.
Okay.
All right. So for everybody watching, check out the description below. Therell be all kinds of extra information down there. If you haven't subscribed to our channel, please do so. Click the notification bell, comment, share. All those things help with the algorithm. And thank you for following Survival Dispatch News.